Hi, here we're going to look at electron configurations. We're going to look at it in terms of the SPDF electron configurations, and then we'll move on and take a brief look at orbitals. Now, if you look at this diagram here of a high school, sort of pre-A-level diagram of an atom, we've got argon here. And argon has got an atomic number of 18. And that tells me, this 18 tells me argon's got 18 protons, which we've got there. And being an atom, if it's got 18 protons, it will have 18 electrons as well. And it's how these electrons are arranged, which is important. Electron arrangement determines the chemical properties of a particular atom. Now, pre-A level or pre-BTEC or sort of pre any sort of a higher qualification, then you'd write this electronic configuration as 2, 8, 8. And we will call these things here shells, energy levels or shells. Got the first shell closest to the nucleus, then we've got the second shell, third shell furthest from the nucleus. Now, there is a principle called Aufbau principle, and this holds all the way up to the highest levels. The electrons should fill, or must fill, the lowest unoccupied energy level first before it fills a higher energy level. So, if, for example, argon will be 288, it's not going to be something like 189 or something. It is going to fill the first two. These electrons are going to fill this before they start filling this, and that's the Aufbau principle. Now, what we can do is we can sort of modify and improve our theory of electronic configuration by introducing the idea of these shells have now got subshells. Sometimes you may see these called principal energy levels. And these principal energy levels now give a number. So now this is the first shell, but we actually now call this the first principal energy level, and that is given a number, and that's given a 1. Now, these principal energy levels, or shells, are split into sublevels or subshells. The first principal energy level, and I've made a little table up here, has 1 sublevel. And the sublevels are labelled S, P, D and F. And here we've got an increase in energy. So the S sublevel is the lowest energy and the F sublevel has got the highest energy. And any principal energy level will always fill an S sublevel first. So we've got the S sublevel, and the S sublevel holds a maximum of 2 electrons. So now I can write 1s2. So instead of this being 2 in my first shell, if you like, we're now saying that we've got the first principal energy level and it's got a sublevel of S, and 2 electrons can go in the S sublevel. And that's it. We need to now move on to the second shell or second principal energy level, because we only know the first one only holds 1 sublevel, and that's the S. So now I'm going to move on to this number 2. Remember, we've always got to start with an S. Always got to start with an S, and the S can hold a maximum of 2. So, the second principal energy level happens to have 2 sublevels. The second sublevel after S is P. So what we can do now is we can fill in this as being 2P. And hopefully you can see now, remember the second principal energy level, they can only hold 2 sublevels, and it's the S and the P. And hopefully you should be able to see how many electrons the P sublevel can hold. To make it this 8, then this must hold 6. So the P sublevel holds 6. We can then move on to the third shell, third principal energy level, that's a 3. again, we have to start with S. And that's going to have 2. And then we go to 3. And that then will be P. And then that will be 6. Now, what happens after argon? This is where we're going to look at the periodic table. What happens after argon, which is here, atomic number 18? After argon, we go to potassium. But potassium is in the S block. We call this region I've shaded in blue the S block. And what we do now is, this is potassium. Now, the third principal energy level actually holds 3 sublevels. And you may think, well, the next one would be 3D. But by some little quirk, what actually happens is, and I'm just going to fill this in now, this is just so happens to be 4. What happens now is, instead of filling this 3D, it actually fills a 4S first. And we say that's 4S1. And this can be shown from the periodic table. It's in period 4, it's in the S block, and it's the first element in the S block, hence it's 4S1. Calcium then would be 4S2. Now what happens is we go back and fill in this third sublevel in the third principal energy level, which is the D. So the next element along after calcium is scandium. So scandium then would go 4S2. Now it goes back and fills into 3D1. And that again is now, it's in the D block. And it's the first element in the D block. So the D block, though, is always 1 behind this number. So that's 3D1. And we can go all the way along. And zinc then, let's just do what zinc would be. Zinc would be 4S2, 3D10. So if you count across there, you've got D1, D2, D3, all the way to D10. And that then backs up the number of electrons in a D sublevel. That is equal to 10. So we can look at the pattern of the periodic table. So the S sublevel we've said holds 2. That corresponds to these 2 elements in the S block. My P sublevel holds 6, which corresponds to my 6 in the P block. My D sublevel holds 10, which corresponds to this 10 elements in the D block. If you count these along in the F block, you would count there 14. And that is exactly how many electrons a D sublevel holds. So we can kind of tell where the highest energy electron is from its position in the periodic table. So for example, this is it is simplified. If I look at this, say selenium here, selenium we can see is in period 4. It's in the P block, and it's 1, 2, 3, 4, fourth element in the P block. So selenium then would be 4P4. That's what its highest energy electrons would be. So that would be selenium. Now, this is just a simplified rule. It doesn't always work, particularly for these transition metals. They tend to behave in a strange way, and they don't always follow this rule. But it's quite a nice rule for looking at where sort of S and P block elements, what their outer electrons, where they're going to be found. What we're going to move on to now is we're going to look at orbitals. And orbitals is a regions of space where electrons are likely to be found. They're probabilities of where the electrons would be. They are not just spinning around a nucleus. In reality, we can think now of electrons as regions of negative charge. And this region of negative charge can occupy a certain volume, a certain space around the nucleus. Key is that each orbital holds a maximum of 2 electrons. If that's the case, we can fill this table in. The S sublevel we know has got 2 electrons. If each orbital can hold a maximum of 2 electrons, there must all be one S orbital. The P sublevel can hold 6 electrons. If each orbital can hold 2 electrons, there must be a total of 3 p orbitals. 3 times 2 is 6. Hopefully you can see how many orbitals a D sublevel would have. It would have 5, and an F sublevel would have 7. Yeah, so it's 1 times 2 is 2, 3 times 2 is 6, 5 times 2 is 10, 7 times 2 is 14. So these orbitals are regions of space around the nucleus where the electrons may be found. So for example, a 1s orbital, s orbitals are always spherical. So 1s orbital, for example, would be a spherical shape like so. Now a 2s orbital Now, the 2s orbital has got higher energy. It's got a higher energy. Because it's got more energy, it can get further away from the attractive force of the nucleus. So this 2s orbital has got like a bigger region of space it can occupy because it's got a lot more energy. So a 2s orbital would be a bigger sphere. So what we're basically saying is that the 2 electrons in that 1s orbital, so it's in effect, it's like saying these 2 electrons here, they could be anywhere within this region of space. So in effect, you've got, I can think of a little electron and a little electron. In effect, what they're doing, they're moving around really, really quickly. We don't know where they are. We just know there are 2 electrons somewhere in this region of space. Same thing with a 2s orbital. Again, we know there are 2 electrons somewhere in there. So this like corresponds to my 2s here. Again, because they've got more energy, they can get further away from the attractive force of the nucleus. So they've got a bigger region of space that they can occupy. Now, the 2p orbitals, they have got a different shape. They are what we call dumbbell shaped. So, for example, the px orbital, so this lies, we would say this lies along the x-axis. So we'd call that px. This then would have, I'll just do this in blue. Again, what we're saying then is there are 2 electrons somewhere, and again, they could be both be in this lobe here, or they could be both be in that lobe, or could be one in each. So they could be both in there, could be both in there, or there could be one in here, one in here. It doesn't matter, it's just region, basically 2 electrons are somewhere around there, like a cloud of negative charge somewhere in that volume. You've then got py, so you can think of these as being lying along the y-axis. And again, there is 2 electrons somewhere in this region of space here. And then we've got our pz electrons. And that lies along the z-axis. So that's kind of coming out in front of you and behind you. We'll call that pz. So all these p orbitals are at right angles to each other. Okay, so we've got our one s orbital, 2s orbital, and there with my 2p orbitals. So for example, in a carbon atom, we would potentially have these orbitals. So carbon, for example, which you should know is 1s2, 2s2, and then 2p2. Again, let's just go back to our periodic table. That kind of matches, doesn't it? Because carbon here is in period 2, it's in the p block, and it's the second element in the p block. Remember, that doesn't always work for every element, but it certainly works for the first 36 elements. What we can say then in carbon, if we were to look at what a carbon atom looks like, instead of it being like the old planetary model, which we've got for argon here, what we can think of now as the electron arrangement, or the pitch of an atom, we can now think of it as being, right, well, I've got a 1s orbital here. I'll just do it a bit neater. 1s orbital there. And that's where these 2 electrons could be found. I've got a 2s orbital, which is where these 2 electrons could be found, and then I've got a py, a px, and a pz orbitals. Now, these orbitals can be represented by boxes. So we call these spin diagrams. So if I was going to draw the spin diagram for carbon, again, what we've got then is these boxes. So that box there would represent my 1s orbital. And we represent these electrons by a spin up and a spin down. My 2s, again, is represented by a box. Each orbital is a box. That's my 2s, and that's my spin up, my spin down. And then my p, again, they've now got 3. This would be like my 2p. That could be like my x, y, and z. Now, the key is here is where do these electrons go? Now, a rule called Hund's rule will say that the electrons will occupy an unoccupied orbital before they pair up. So what that's saying is that you will get the electrons, one going into the x, if you like, so one going into here, and then one will go into the y. So you'll get this. So they will not pair up into orbitals unless they're already filled. So that would be the correct way, and obviously this, therefore, that would be wrong. Because these two, they don't particularly want to be near each other. They're both negatively charged, so this one will be thinking, actually, I've got a free space there. And I'll just jump onto that. Okay, and that would be my spin diagram for carbon. So that there gives you a brief overview of electron arrangements and orbitals. Obviously, this is a very brief overview. Further reading will be required and practice will be needed writing down all these electron arrangements. It is important to look at these orbitals and understand them because these orbitals then overlap and that's how you produce your chemical bonds. So that there, guys, is electron configuration.